Welcome to ES310 Lesson 21. Today's lesson will be a brief overview of relative velocities and accelerations when the coordinate systems are rotating as well as translating. Our last two lessons have looked in depth at situations where we have relative velocity and acceleration due to translation. Today we will be adding the rotation component of those equations. So by way of a brief overview, the motivation for learning this material is that this is what we need in order to analyze systems which slide at contacts, where they're not connected by a pin. This is also how we analyze the relative motion of 2 points that aren't on the same body but are on connected bodies. And this will help us analyze motion along a curved path. The details of the derivations of these equations are found in the textbook. However, we can write the relative velocity equation for the point of interest being equal to the velocity due to translation of the origin of the new coordinate system, so point A, which is where little x and little y is, plus this second term, which is due to the rotation of that coordinate system, plus velocity of B relative to A, so the velocity of B within the coordinate system of the little x, y, z coordinate system. The acceleration has even more terms but comes from the derivation of this velocity, so you've got your acceleration of B equal to the translation of B, and then the acceleration due to rotations of various types, and then the accelerations due to motion within the rotating coordinate system. Definitions and notation conventions: the capital X, capital Y, capital Z coordinate system is the stationary coordinate system fixed at some origin. The little x, y, z coordinate system is the one that is rotating and translating. And omega, capital omega, is the angular velocity of that rotation. So, as far as a motivating example, these equations allow us to analyze some very interesting effects, one of which is the Coriolis effect, which causes the spinning of hurricanes and tornadoes, the wind patterns, as well as things like what we see on this merry-go-round.
To an observer above the merry-go-round, the path of the ball appears straight, while to someone sitting on it, the ball appears to curve to the left. This exemplifies the Coriolis force, whereby, to an observer on the rotating Earth, the path of an object appears to be deflected, and this is a result of the Earth's rotation.
So, let us take a look at an example of how we would solve equations or solve systems using these equations. So we have a rotating platform that is rotating with an omega and an alpha given in the problem. So omega is 0.5 and alpha is 0.2, and those are in the positive direction. And we have a girl walking on that rotating platform, and for our situation, she walks from A to D and then on to C. So she's walking straight across the platform. We are to figure out what her acceleration is at point D. So we have two parts of these systems, right? We have the platform itself, and we have information about its motion, and then we have the girl relative to the platform. So if we look at the platform itself, we look at its center, the acceleration of its center is 0 because it is fixed on an axis. Its rotation, omega, is equal to 0.5, which in this case is the rotation of the moving coordinate system as well, so it's this capital omega. Alpha of the platform is 0.2, which is the angular acceleration of the moving coordinate system, which is omega dot. Now the girl relative to the platform is moving at a constant speed, so v dot is equal to 0, and a speed of 0.75, and her the direction of that speed is in the positive y direction, so that's j hat. Both of these are in the k hat directions, right, out of the plane. So we've got this v, and then we have the radius of the location of the girl, so that's point D, relative to the origin of the turning coordinate system, which is point O. And in that case, that is D in the positive x direction, and D is 1 meter. So we've got 1 I hat. So now this is all of the information we need in order to solve these problems. So we can start by writing out we're looking for acceleration, so let's write out the acceleration equation. We have A of the girl at point D, so let's call that AD, is equal to A of the origin of the rotating coordinate system, so that would be AO, plus omega dot crossed with R of D relative to O, also a vector, that one's a vector as well, plus omega, the vector, crossed with omega, the vector, crossed with R of D relative to O, plus 2 times omega crossed with V of the girl at point D relative to the origin, and this is in the XYZ, so relative to the rotating coordinate system, or the platform in this case, plus the acceleration of D relative to O, also measured in the XYZ coordinate system. So in our case, some of these things go to 0. The platform is not translating, so the acceleration of the center is 0. And the girl is not accelerating relative to the platform because the velocity was constant, so that is also equal to 0. So then we just get to plug in all of these other known values. So we got omega dot, which is 0.2 k hat, crossed with R d of O, which would be 1 I hat, plus 0.5 k hat crossed with 0.5 k hat crossed with 1 I hat, plus 2 times 0.5 k hat crossed with 0.75 j hat, plus 0. Alright, so now we have some cross products to do. So k crossed into I, we've got a positive k crossed into a positive I, which gives us a positive j, so that's 0.2 j hat. And then here we've got 0.5 k hat, we're going to do the part inside the parentheses first, crossed with 0.5 k hat crossed into 1 I hat, so positive k crossed into positive I gives us positive j, so 0.5 j hat, plus 2 times 0.5 is 1 k hat crossed with 0.75 j hat, so positive k hat into positive j hat gives us negative I hat, so minus 0.75 I hat. Then we're going to do this last cross product, so we have 0.2 j hat plus 0.5 k hat crossed with 0.5 j hat, so positive k hat crossed with into positive j hat gives us negative I hat, and 0.5 times 0.5 is 0.25 I hat minus 0.75 I hat. So put these together, we get 0.25, 0.75, that's negative 1 I hat plus 0.2 j hat. So most of these problems, though the equations are very long, if we can set up the motion of the platform, the motion of the object relative to the rotating coordinate system, where the platform's a coordinate system, then it's just a matter of plugging these values in and taking a whole lot of cross products of i's, j's, and k's.